Okay, today we're going to talk about cubic, square root, and reciprocal functions, and then we'll actually finish out this section for sure. I have the homework check for 1.5 as Thursday, 1.6 as Friday, and so I've kind of pushed back a few things. There is an issue now with your test for mid-quarter. Right now it is planned as Wednesday, October 3rd. And probably on tomorrow's recording, I will say when that's going to be for sure. But right now, I am a little uncertain. So we're going to look at these three things, and I am just going to write these out as we go. And these are our parent functions. So the first one is the cubic function. The cubic function as a parent function, and that is when f of x equals x to the third. And I will, I'm going to sketch a picture just on, without graph paper. Oh, that was not the best indicator of that. And just to kind of see what that looks like. I'm not going to get very far here. But if I plotted some points, 0 to the third is 0, 1 to the third is 1, 2 to the third is 8, so it would be kind of up there already. Negative 1 to the third is negative 1, negative 2 to the third is negative 8. And so you get that cubic equation that looks like that. So you want to have, in your notes a fairly decent graph of that. If you want to write it on graph paper, that's maybe a good idea as well. And so we're going to go through all the characteristics of these functions. I think we did that on the linear and the squared function, but we'll go through hopefully everything, and then I'll just check that I have everything. The domain, as we walk along the x-axis, no matter, even if we're at negative infinity on the x-axis, we would see a y value way down there, and we step on it at 0, 0. As we go across, it's everything. So from negative infinity to infinity, the domain is all real numbers. The range, likewise, for this one, unlike a parabola that has that U shape, this one has kind of the U is flipped down on that left side of the y-axis. So we get all real numbers. As I'm walking along the y-axis and look left and right, I see that function everywhere. So the range is from negative infinity to infinity. And this function is odd in two ways. We know that if I put f of negative x, I get negative x to the third, so it's the opposite. And graphically, if I rotate it about the origin, then it would have that symmetry. So it is odd, and it has symmetry with respect to the origin, symmetric with respect to the origin. The x and y intercept are at that point 0, 0, so it has one intercept, which is at 0, 0, and then increasing, decreasing, or constant. And do you agree that it's increasing everywhere? And it's increasing along its whole domain. So it's increasing only, increasing, and in the interval negative infinity to infinity. Just a reminder, those intervals are always with parentheses. In this case, it's from negative infinity to infinity, so they have to be. But just in general, I'm just going to put that down a little. Just in general, it is always in parentheses. Any questions on the cubic function? We're pretty familiar with that. And so then our next one after the cubic function is going to be the square root function. So the square root function. And if I miss anything as we go, I will check it on the other slides, but we'll try to make sure that we come back here and kind of look at things. So the square root function, I'm going to just make sure that this positive x-axis goes to like 4. 1, 2, 3, 4, and 1, 2, 3 is good there. And it really doesn't matter what I have for negatives. So the square root function is a little bit more interesting, or something that we have to use a little more care when we find it. So if I just think about making a table of values, or in my head, if I put in 0, the square root of 0 is 0. If I put in 1, the square root of 1 is 1. And then I'm not going to pick 2 or 3 because they're not perfect squares. But if I pick 4 for x, the square root of 4 is 2. So I can plot the point 4, comma 2. And I would say generally those are kind of the points that we would plot. And it's like a half of a parabola. And we talked right at the end of the hour, it's not excluding the negative values in the radical, because those would be undefined or not real answers. But it's actually taking that negative square root. So this is, so you don't want to draw this, but if I did the negative square root of x, that would be, the rest of that parabola. And if you remember, if y equals x squared, then x equals the plus or minus square root of y, as we would do that. So we don't use that because that would keep it from being a function. But we, at this point in our math life, want to just kind of be aware of that. So ordinarily, I was going to ask you a bunch of questions, but since I'm recording this, do you agree domain? What is the lowest value of x we can have? 0. Yep, 0 is the lowest value, and then I can go to positive infinity. For the range, what's the lowest value I can have for y? 0 again, and so then from 0 to infinity. So our domain, and that 0 is included, so we can do that, 0 to infinity. And our range is 0 to infinity. And I will tell you that sometimes these are both called non-negative reals. And I'm just going to write that as well. Non-negative reals. So we don't call them just positive reals because they include 0, and so non-negative reals. The x and y intercept is a single point at 0, 0, so we just call it the intercept. Intercept is at 0, 0. So if you were asked specifically to list the x-intercept or the y-intercept, they would be given as the same point or answer. Increasing, decreasing, or constant, what is it? What's happening the whole time? It's increasing. So it's increasing along its whole domain, which is from 0 to infinity. But we do write that again as an interval, and we don't include the endpoint. So even though the domain included 0, the interval along which it's increasing is with a parenthesis, 0 to infinity. So it's increasing there. And is there anything I had on the other one that I haven't put on here? I think I'm good to go. And then, so those are probably the most familiar to us. And really the reciprocal one should be as well. The reciprocal function, which is f of x equals 1 over x. Just keep in mind that is the same as x to the negative 1. And so 1 over x is the same as x to the negative 1. When we graph this, and I'll just put a couple points on here. When I graph this, it's 1 over x. And so let's see. It's really hard to plot points for this one. first we'll notice if we try to put 0 in there, 1 divided by 0 is undefined. So it is going to have some asymptotes as well. We'll maybe write those a little later. And if I think of a table of values, well, if I put in positive 1, I would get 1, 1. So it does hit that point. If I put in 2, it would be at 1/2, so I could kind of plot that. And if I put in 1/2, do you agree it would be 2? And I'm just going to do that. F of, and I'm going to erase this, but I'll just put it up there. So F of 1/2 is 1 over 1/2, and then that's 1 over 1 times this 1 that's in the numerator times, I flip that upside down, 2 over 1. So 1 over 1/2 is actually equal to 2. So I can plot at 1/2, I could go up here to 2. And so those are a little kind of awkwardish to plot exactly, but the same thing happens if I put in -1, 1 over -1 is -1. If I put in -2, I get -1/2. If I put in -1/2, I get -2. And then visually, I'm kind of a little challenged to draw that, but there, that's going to be as, oops. Oh. So these go exceedingly close to the X and Y axis, but they never actually touch the X and Y axis, even if mine look like they might be touching the axis. So then our domain, as I step along the x-axis from -infinity, I'm -infinity, I look down and there are values, 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 values. They're getting further and further away. When I step on 0, I look up and I look down. Do I see the function at all? No. And so that is not defined there. And then as I walk along, I'll see it again to infinity. So this domain is listed this way, from -infinity to 0, but with an open parentheses at 0. So from -infinity to 0, union with, so it's kind of in two parts, union with, and then as soon as I hop over 0, I see it again, but I don't include the 0 again, 0 to positive infinity. And that's the way we say all real numbers except 0 is kind of what's happening. The y-axis, same thing, -infinity up to when I get to 0, there's nothing there, but then as I go up there, I will have it again. So the range is the same from -infinity to 0, union with 0 to infinity. Oh, I did forget to address something in the last one. I'm thinking of it right now. Back at that square root function, was it even, odd, or neither? Back at the square root function, I will go back to this. Is this even, odd, or neither? It's neither, because it's not defined for negative values of x. It's not even or odd. It's neither as we go. So we're not commenting on it. But this one, even, odd, or neither. What do you think? This one is odd, and it's symmetric with. Oops. Symmetric with respect to the origin. Increasing, decreasing, constant, or some I don't know, some conglomeration of that. Do you agree that from -infinity to 0, it is going down, correct? And so then it has that weird thing that it goes down to -infinity there, but as soon as we cross over here, if you think of 1 over a million, right? 1 over a million, which would be an x value. F of 1 over 1, 2, 3, 4, 5, 6. 1 over a million would be 1 over a million. 1, 2, 3, 4, 5, 6. And so that would be 1, 2, 3, 4, 5, 6. That would be a million. So if I went to 1 over a million, I couldn't even see that, I don't think, right? But my point would be at a million, and I can't, fit that on my board either. So it has that weird characteristic that as it gets closer to zero from the left, it goes to negative infinity. But as soon as we hop over there, boom, it is up at positive infinity and it's coming down. So it actually is decreasing everywhere. Do you agree? It decreases in this part and it decreases there. But since it's not defined there, we can say it's decreasing in its whole domain or in there. So it's decreasing in the interval from negative infinity to 0, union with 0 to infinity. What are its intercepts? No intercepts. So no intercepts for this one. No intercepts. And symmetric with respect to the origin. And how about increasing, decreasing? We have that. And I think that's everything that we want to have for that one. And then I'm just going to go through the next couple of slides, which kind of give all this information. But in my mind, they take too many pages of slides. So I like to kind of write it all on one page. And then if I need to add anything, you're looking at your notes while I go through the slides, and then just let me know if I missed anything, and I'll add it back in there. So this is first the cubic one: domain all real numbers, range all real numbers, odd, intercept 0, 0, increasing negative infinity to infinity, symmetric with respect to the origin, and here's the beautiful picture the book authors put. And I think did we have all that? And then the next one, is the square root function. F of x equals the square root of x. Domain, all non-negative real numbers. Range is the same. Intercept at 0, 0, increasing from 0 to infinity, and with a parentheses, and there it is. And the reciprocal function, domain negative infinity to 0, union 0 to infinity. Range is the same, odd, no intercepts, decreasing in the interval that is the domain, or domain is really what they're using there, and symmetric with respect to the origin. And there is the reciprocal function. So those are pretty standard for us. Next is step and piecewise defined functions. So these are probably less familiar to us. And to be super honest, I don't know that the little calculators do the greatest integer function. I just don't know. So somebody could look that up, look on there, in some of the little menus. But I will go through what the step function is as we do that. And a piecewise defined function, we don't have really a parent function for that because it's has two different functions. So it might be a combination of two of these that we've looked at or whatever. But I will do a piecewise defined function with just two linear functions, just to kind of see it and kind of remind us of what that is going to look like. And so the step function is the one that we'll look at first. Step function. And it's like when you go in a parking ramp or a garage where you're paying kind of that hourly fee. And the reason I say it's kind of like that is the parent function for a step function from 0 to 1 is 0. And really, if you're going in a parking garage, they're not going to let you park for the first interval free, generally, Although, now that I'm saying that, in the Baltimore Washington International Airport, for a long time they did let you do that because they didn't want people driving through that loop. You know what I'm talking about, like where people drop everybody off or whatever. They didn't want people to do that, so instead they would let you park free for the first whatever their increments were. never mind. And the basic step function is the greatest integer function. Greatest integer function. And a lot of times that's unfamiliar to us, and it is f of x equals, and here's the best way I can explain it is just by drawing this little x, and it's kind of like a bracket with a double bar is the way I think I like to write it or think of it. So it's like a bracket with a double bar, and it is the greatest integer less than or equal to x. It is the greatest integer less than or equal to, oops, less than or equal to, or equal to x. So for this, this one I think just deserves a little extra attention. Is that okay if I don't just go right to domain range graph and just kind of, I think it's worth kind of looking at some problems. And actually I'm going all the way back to just having a little number line. So I'm going to do a little number line, -4, -3, -2, -1, 0, 1, 2, 3, and 4. And then we'll just do a few problems. So do you agree that the greatest integer of 2 is just 2? Because the biggest integer less than or equal to 2 is 2. And we'll do a couple other kind of easy ones. The greatest integer of 2.5 is also 2. Do you agree? Because it's saying, what is the biggest integer less than or equal to 2.5? Do you agree that it's 2? Yes? Equals 2. And so I'll just stick with this 2 theme. The greatest integer of 2.9, what would that be? 2 again, right? So it's very easy when it's positive numbers because you just drop off the decimals or any remainders or anything like that. It's a little trickier though when it's negative. And so if I want the greatest integer of -1/2, what is the biggest integer less than or equal to 1/2 or -1/2? So there's -1/2. What is the biggest integer? Well, okay, let's go back to these. If I plotted these here, if I plotted 2, 2.5, and 2.9, the biggest integer was 2 there, right? So now if I'm at -1/2, what is the biggest integer that is less than or equal to -1/2? It's actually -1. So do you see how negatives are going to be a little trickier? Right? So let's just do the greatest integer of -3.6. What's that going to be? I'm at -3.6. What's the greatest integer? -4. -4. So do you see why I wanted to kind of do a little more exploring of that one? Because that is, that is a little trickier in our minds. So that's the greatest integer function, and that's just kind of helping us set that up. And now graphically, this is what it'll look like. 1, 2, 3, 4, 2, 3. And I'll do some negatives and some positives, but I have to just kind of get it on there at first. So what is the greatest integer of 0? 0. Do you agree? Because if it's an integer, or it's just that number. And then as I'm at 0.1, 2, 3, 4, 5, all those decimals, it's still there. And then when I get to 1, what's the greatest integer of 1? Less than or equal to 1. It's 1. So it's going to hop up there. So what is going to happen? It's going to get super close there. So that's an open circle, and then at 2 it's going to hop up to 2, and at 3 it's going to hop up to 3, but between these it's going to be, there we go. So it is a function, Because there's only one value. You know, it doesn't have two values there. It's always open at the bottom one and then filled at the top one. And same thing here then if you graph it this way, you know, kind of going backwards. At 0, it's not defined as that, but and negative a half, negative 0.9, negative whatever is all going to be negative 1. Open circle here, and it goes like that. Kind of as we look at that. So that one is just a little more like, you know, challenging as we kind of look at it. And let's kind of see what we can say about it. What's the domain this time? Think about that. Walk from negative infinity to infinity. When you look up or down, do you see it all the time? Yeah, so like, you know, I won't go all the way to negative infinity, but I'll kind of be in here. When I'm here, it's right there. When I'm walking along here, it's still at that same spot. When I step here, I see it there. It's not there though. And that's important because then there's only one y value. So the domain is actually all real numbers as we look at the greatest integer function. And so from negative infinity to infinity. Now, the range is not that way. Do you agree? Try walking a moment. Imagine you're walking from the negative infinity to positive infinity on the y-axis. And I'll walk along there as well with this green pen, but then I'm going to get rid of it. And so I'm at negative infinity, whatever's happened. So as I step on negative 2, do I see the graph? Yes. But as I step off of negative 2, do I see the graph anymore? No. But when I step on negative 1, do I see it? Yes. When's the next time I'll see it? 0, and then 1, and then 2, and then 3, and really I saw it at negative whatever. So what are those? This is like negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. What kind of numbers are those? But they can be negative. Whole would be their integers. So the domain is the set of all real numbers. The range is the set of all integers. And actually, I'm going to pull off those little dots. So let me do that first. And I'm going to give a descriptive range of that. The range is the set of all integers. And we can call that, you know, we can call that by its number set if we want, or, you know, for now, I just want to write it as the set of all integers, just to be careful. Does it have any intercepts? And so let's talk first. The easiest one is the y-intercept. What is the y-intercept? 0, because it hits right there. So the y, and you know, before we've said that the intercept was 0, 0. But do you agree that there's more x-intercepts? So this is only the y-intercept, and that is at 0, 0. So the x-intercepts are kind of unique because the x-intercepts are in that interval from 0 to 1, where we include 0, but we don't include 1. So the x-intercepts are in the interval, and we give, you know, the x interval. In the interval from 0 to 1, because it's all those points along there, we have everything in that interval. It does include 0, so even though this is an interval, it's an interval of intercepts. So it is specific points. So even though I've said a lot of times we don't use the bracket for the interval, in this case we do because it includes that 0. And we're not saying that it's increasing, decreasing, or constant. So that is from 0 to 1. But it doesn't include the 1 because then 1, it hops up past there. And, you know, sometimes we just say some things about this and just, you know, note what is happening. Because this is not a continuous function. Do you agree with that? It does not have continuous flow as it goes along. And so we say things like it is constant between pairs of integers. Between pairs of integers. So, you know, it has that constant dynamic, and we can't really exactly list that out. And then it also jumps vertically one at every integer. So it jumps vertically 1 unit at each integer. As we look at that. And then I just am going to put a piecewise. A piecewise function doesn't really have a parent as such, but I'm just going to kind of have an example of a piecewise. P-I-E-C-E-wise. Piecewise function, and I'm not going to call, since it's not a parent, I'm just going to call it an example. So this isn't necessarily a parent function, it's just an example. And I'm just using two linear functions because it's going to be just the easiest. So f of x is equal to either -1/2 x minus 6 for x less than or equal to -4, or x plus 5 for x greater than -4. Whoops. And definitely, I would suggest if you're going to graph something like this, that you make a table of values so that you can, you know they're both linear. You're just going to connect a bunch of dots, and then I think I just went to -6 or something along here, and I'm just looking at my values here. Ooh, those are not equally spaced. Sorry. So I'll work on that a little bit. So this one is from negative infinity to -4, and so for this piece, and I'll do them in two colors. I'll make a little table of XY values, and the values I used were -6, -5, and -4. Even though that's not going to be a whole number, it's not that hard to do. -1/2 times -6 is 3. 3 minus 6 is -3. Did I do that right? Check me. This is 2.5 minus 6 is -3.5. That makes sense. And at -4, it's 2 minus 6, -4. And then I'm just going to plot those points. 6 at -6, it's -3. At -5, and it's -3.5. And at -4, it's -4. 1, 2, 3, 4. And we'll see, it goes like that. And this, it is defined at 4 there, so that we can see it. Then, since -4 is that boundary, when I make my XY chart for this rule, I would figure out what it is when x is -4, but I just want to know that's going to be an open circle there, because it's not really equal to that at -4. Do you agree with that as I look at it? And so I did -4, I don't know. For some reason, I did -1 and 0. It doesn't matter. If I put in -4 plus 5 is 1, -1 plus 5 is 4, 0 plus 5 is 5. And so this other piece of this at negative 4, 1, 2, 3, 4, I'm at 1, but that's an open circle. At negative 1, 1, 2, 3, 4, I was there. And at 0, I was at 5. And these do go, you know, kind of on forever. So what's the domain of that? Is it still all real numbers? Because as I'm walking along here, I'm seeing the green function, green, 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 green. When I get here, I still see the green one and there's nothing at the red one. And then as soon as I step by, I'm going to see the red one. So the domain's all real numbers. What is the range? Is it all real numbers? I'll ask that question. I don't feel like it is. So keep in mind, this green line is going to positive infinity, and this red line is going to positive infinity. So I think it's going to positive infinity. When I'm at 1 here, there's nothing there. But is the green one over there? Yes, so I'm good to go there. What is the lowest I can be as I walk up there? Negative, it was a 4, 1, 2, 3, 4. Yeah, so the range would be from negative 4 to infinity. Does that make sense to everybody as we go? So those are the functions. And generally, you know, we can do increasing, decreasing if we have to. And generally, they're not going to have symmetries because they're like two different rules. And it's unusual that they would both be linear, but let's face it, linear was easy for me to just do a little example of. And so that's what I did. So let me just go through the slides. I'm going to go kind of quickly because we should have everything I think that I want on here. Does anybody need to see this picture anymore? Okay. So step greatest integer. We talked about what the greatest integer looks like. Here's some examples of greatest integer. We did our own. Here's the picture of it. Domain, all real numbers. Oops. I don't know why it's not moving ahead. So, oh, there we go. Range, y-intercept, x-intercepts on that interval. The graph is constant between consecutive pairs of x values. Jumps vertically at each integer value of x. Then this is just an example. Just a reminder, the greatest integer, you figure that out, and then you're adding 1 to it. And just, you know, I don't know that we'll even do that one, but we'll sure look at it. So for that one, this is the one to kind of be careful of, is the 1.5. The greatest integer is 1, plus 1 is 2 for that one. And this is what that looks like. Notice it's added 1, so it kind of almost pushed it back that way a little bit. And then here are all the parent functions, but you should have them. Did we draw a constant function? I sort of forget because that was yesterday. Yes, and an identity function. Oh, we did not do an absolute value function. So then let me look at square root function. And I'm just going to go to this next one and then I'll back up. We did a quadratic, a cubic, a reciprocal, a greatest integer, familiarity. Okay, but you need to add an absolute value function. So that's the one that isn't in there. Can you add those parts yourself? And I won't go on to 1.7 today. Well, because I obviously didn't have time. Do I need to go back to this slide tomorrow or not? Okay, so don't forget to add the absolute value function. I'll just say it that way.